Okay, awesome. I think I have a much better understanding of the confusion. So let's look at, again, this situation where we have log base A of B equals X, and its equivalent statement, which is A of X equals B. Now, what you did was you created a tautology where X equals X and B equals B, and then said, well, X does not equal B. And that is very true. X does always equal X. B does always equal B, but X does not equal B. Check, check, and check. If we look at these, though, that is very apparent. This X does equal this X, and this B does equal this B. They are the same and can be interchanged. So let's look at that for a second. So instead of saying, well, B equals B, let's instead say, okay, I'm going to let B equal what it does here in this case, which is A of X. Okay, so I'm going to replace, which is totally valid, I'm going to replace B in this form. So I'm going to substitute, and now I will have log of A of X equals X. So now, using simple substitution, bing, bang, boom, here we are. I don't want to make this much more clear. Okay, so now using one of the rules of logarithms, there's a couple ways to look at this, but I can pull this X out front as a multiplier. So a rule, as you, I'm sure, totally understand, is simply something that always works in mathematics. Okay, so I can pull this out, and you'll see it done different ways, but doing this, I get X times log base A of A equals X. So now I get this X multiplier in front. Well, log A of A, if I resolve this part, which means transform this into its numerical value, that numerical value is going to be 1, right? What would I need to raise A by to get A? Well, 1. So this part resolves to the value 1. So now I have 1 times, or X rather, times 1 equals X, which then is X equals X, which is, again, true. So there is the equivalence, X equals X, but X does not equal B. And I could go the other way. Let's see here if I can do that. So I can take log A of B equals X, and A of X equals B, and now I can substitute X for X, and what I will get is A of log base A of B equals B. And now we have another idea or rule where a base raised to a log of the same base. I don't remember the name of it, but basically this resolves to just b. And again, I have b equals b, which is true. The other one was the power rule. I don't remember what this rule is called. So maybe that sheds a little light on what you were looking at. So now let's look at this conversion, this equivalence conversion. And it is in a sense the inverse, but this equivalence is just what allows us to rewrite the equation into a more workable form. If I had, let's say, I'm going to make this up, so it's going to be terrible, 8 raised to the x equals 2, which is not great because I can already tell, right, I'm going to have a fractional number, and it's not going to be power, and it's not going to be great. But what this allows me to do then is say, well, I can't just off the top of my head know what x is, so I'm going to convert this to its equivalent form, where I have x equals log base 8 of 2. And I could plug that into a calculator, and I'm going to get this fractional result of what x might be. Let's see here. I think that's going to give me a third. X equals 1/3. And if we plug that back in, we can say, okay, 8 to the 1/3. This is a root. Right? I can use its equivalent form and rewrite it as the cubed root of 8 to the first power, and that makes sense, right? What would I have to multiply by itself 3 times in order to get 8? And that would be 2. 2 times 2 times 2 gets me 8. Therefore, the cubed root of 8 is 2. This is another one of those equivalence ideas that I can rewrite fractional exponents as radicals, which you were using that idea in your triangular relationship concept. I hope this didn't add more issue. I'm going to do another video on the actual inverse stuff and the graphs if you're interested. Hope this helps.